Hello everyone, welcome to my YouTube channel SGKmistry Lectures. In this video, I'll be explaining about industrial organic chemistry, and in specific, I'll be explaining about dyes. So this video will cover the following topics: the characteristics of dyes, the classification of dyes based on the application on the fibers, color and constitution, in which we'll be discussing about Witt's chromophore-auxochrome theory, and also I'll be explaining about the synthesis of dyes, which will include the synthesis of malachite green, Congo red, alizarin, and indigo. So let us start with our topic. So firstly, we have to know what are dyes. So that is important. What are synthetic dyes and how they are different from just colored compounds. Okay, so synthetic dyes are nothing but they can be defined as a colored substance. So first of all, they have to be colored, right? Because they are dyes. So when you apply these substances on the fabrics, they should impart a permanent color to the fabric. Okay, this is very important. Permanent color should be imparted to the fabric, and this color should not be removed by washing with water or in the presence of soap or on exposure to light. So mainly these dyes have to apply themselves to the fabrics so that they have to impart the color to the fabric. And another thing is that these are the main conditions. This color should not be faded away or it should not be removed in the presence of water, soap, or in the presence of light. So these are the main conditions for which a particular compound can be called as a dye. Now, why cannot all the substances, we know that in chemistry there are so many colored substances, right? Why can't you use these colored substances as dyes? Why there are only certain specific compounds which are used as dyes? Okay, so for example, we know that picric acid as well as trinitrotoluene both are yellow in color, right? But we don't use these as dyes. Why don't we use? Because they do not fix the color to the cloth. Okay, so they do not permanently impart a color to the fabrics. So that's why we cannot use these compounds as dyes, although they are colored. Now, talking about the characteristics of dye. So already we have discussed a few characteristics. What are the main conditions for a particular compound to be called as a dye? So let us discuss about the characteristics of a dye. First of all, it should impart suitable color to the fabric. Okay, the fiber or the fabric, whatever you're considering, whatever you're taking it. It should resist the action of water. So this is the main condition: water, soap, as well as light. In the presence of these, the color should not be faded away or the color should not be removed off, right? And it should be able to fix itself to the material from the solution. So what we do is we take a fabric, we mix it with the solution of the dye, and then what happens is the dye will fix itself to the fabric or the fiber of the fabric, especially when we are talking about. So it should be able to fix itself to the fabric from the solution. So you're dipping the fabric in the solution of the dye. So the dye has to fix itself to the fabric. So these are the characteristics of a dye. Now, let us talk about classification of the dyes based on mode of application on the fibers. So how do you classify them based on how you're going to apply these dyes on the fabrics? Okay. So first of all, the first category we are talking about is a direct dye or substantive dyes. Okay, substantive dyes or direct dyes. So as the name indicates, direct, that means directly you can apply these dyes onto the fabrics. That is, you're directly taking the solution of the dye, and of course the dye is applied to the fabric. Okay, so these are the dyes which are directly applied to the fabric by immersing it in a hot solution of the dye. So you're taking the fabric, you're going to dip the fabric in the hot solution of the dye, and directly these dyes will apply themselves on the fabric. Okay, they will stick to the fabric and permanently they will impart a color to the fabric. So they can dye cotton as well as wool as well as silk. Okay, so example for such a dye is Congo red. Let us talk about modern dyes. Okay, these are also called as indirect dyes or adjective dyes. Okay, so again from the name itself, it is very clear something indirect. You're not going to directly dip the fabric into the solution of the dye. It cannot impart the color directly to the fabric. So there is something indirect way that is going on in this particular type of dyes. So you can just look into this particular picture so that it is much easier to understand. So here we need something called as a mordant. Okay, and this is nothing but a bridging agent. Okay, so you can see in this picture itself. So here we have the mordant. So of course we have a tissue here or the fabric, whatever you're going to take, which you want to color. And then we have the dye. Okay, and there is a bridging agent here which is called as the mordant. Okay, so what this mordant does, so how is the dyeing process taking place in this particular when we are using this mordant dyes? So here, first thing is you're going to dip the fabric in the mordant solution. Okay, and then you're going to take out the fabric and then you're dipping it in the dye solution. So here directly you're not going to dip uh, the fabric into the dye solution. So first you're going to dip it in the mordant solution and then you're going to dip it in the dye solution so that the color is imparted to the fabric. Okay, so example for such type of dye, the mordant dye is alizarin. Now, here, which type of mordants we have to use? So that is main thing we have to understand. So whenever we are using acidic dyes, okay, we have to use a basic mordant. Okay, the nature, the opposite nature mordants. Okay, so we use more basic mordants like FeOH thrice, okay, aluminium hydroxide, ferric hydroxide, etc. Suppose you're using a basic dye, then you're going to use acidic mordant, such as tannic acid. Okay, so you can see in this particular picture. So what we do is we take the fabric, okay, and first you're going to dip it in the mordant solution. So then you're going to dip it in the dye solution, the solution of the dye, and finally you're going to see that the color is imparted to the fabric. Okay, now let us talk about the third category of the dyes, that is the vat dyes. So here there is something different here. Okay, the first two categories we have spoken that in the first case directly you're going to dip the solution in, dip the fabric into the dye solution. In the second case you're going to use a mordant. Here the twist is that the dyes are not soluble in water. Okay, so you cannot just dip the fabric into the solution here. Okay, because the dyes are not soluble in water. So you cannot directly apply it to the fabric. Okay, so what we need to do? We have to convert it into the reduced form. So you can see here, these dyes which are used for this purpose, the vat dyes, first you have to apply it in the reduced form. Okay, because reduced form is water soluble, whereas as such, these dyes are not soluble in water. Okay, so you're going to use the dyes, okay, to color the fabric in its reduced form, and then you're going to reoxidize the reduced form so that you get the color. Okay, so now how this reducing process is done? It is done in large wooden vats, so that's why we call it as the vat dyes. Okay, so here we are using sodium bisulfite in alkaline medium for reducing this dyes so that the reduced form is water soluble, and then you're going to convert it back. You're going to reoxidize it back to the normal dye. Okay. So you can see in this picture how this particular vat dyeing is done. Okay. Now, what you're going to do, how you're going to dip the fabric, all these things. So you can see in this reaction. So first of all, the example for this particular type of dye is indigo. So first, when you're talking about indigo, so this particular structure of indigo, here we know that it is water insoluble. So what you have to do, you have to reduce it, right? In the reduced form, it is water soluble. So first you're going to reduce this. Okay, you're going to use the sodium bisulfite in the presence of alkaline medium, that is sodium hydroxide. So you get the reduced form, which is also called as a leucoform. Okay, and this reduced form is water soluble. Now, since we know that we need to dip the fabric in a solution, right? So you're going to dip the fabric in this water soluble form of the dye, and then you're going to reoxidize it so that you get the color. Okay, so example for such type of dyes is, one of the most important example is indigo. Now let us talk about azoic or azo dyes. So I hope by now all of you know what is the diazotization reaction, right? So this particular class of dyes, something is related with that of the diazotization reaction. So here, mainly this particular type of reaction is involved here, diazotization reaction. Okay, so here, this type of dyes are synthesized on the fiber itself. So this is again a special type of dye where you're going to synthesize the dye in the fiber itself. Okay, so example again, Congo red. Here what we're going to do, we are going to soak the fabric in the diazonium salt solution, and then you're soaking it in the coupling solution so that coupling reaction takes place, and finally the dye is synthesized on the fabric itself. Okay, so this is how it is going to happen. So here you're going to get the Congo red. So first you can see these are the raw materials what we use. And finally, the synthesis of this particular dye takes place on the fabric itself by using the coupling agent. Okay, so coupling reaction takes place between the diazonium compound and the coupling reagent, so that you get the diazode dye in the on the fabric itself, so that you get the colored fabric. Okay, now there is another class of dyes which is called as the dispersive dyes. So I hope by now you know about the soaps, the micelles, what I used, all these concepts, right? So dispersive dyes, again, these dyes are insoluble in water. So what we do, so here you can see, you use the dye which is in the solid form. Now you're going to use a dispersing agent, okay? So that you make this dye as soluble in water. So what we are going to do, you're going to dip this, you're going to add this dye to the soap solution, okay, which acts as a dispersing agent. Now we know that in the soap solution, there are formation of micelles, right? So we know that a soap molecule, it has a hydrophobic end as well as a hydrophilic end, right? So we know that it has a head and a tail, okay? So how these hydrophilic regions and the hydrophobic regions, how they arrange so that the micelles are formed. Right, so you can see here, these are the, so here you can see these, whatever the around these structures are the head portions of this soap molecule, and they have the tails also, right? So you get the dye micelles, okay? The dye will be in the middle, okay? And it will be surrounded by the soap molecules. The hydrophobic tails will be surrounding the dye molecules, whereas the hydrophilic head portion of the soap molecules, it will be outside. Right. So micelles will be formed. And of course, now, because of the presence of the dispersing agent, that is a soap solution or the soap molecules, you can see that the dye is soluble. Okay. The dye becomes dissolved. Now, again, what is the next step? You're going to dip the fabric. Okay. And you can see that the color is imparted to the fabric. Okay. So these dyes are insoluble in water. Okay, they are insoluble in water. So dye is dispersed in the soap solution, which consists of the solubilizing agent. So the example for this particular dye is 1-amino 4-hydroxy anthraquinone. Okay, so now let us talk about color and constitution. How this coloring takes place. Okay, how do you perceive a color? What is a color absorbed? All these things we are going to understand in detail. So when white light falls on a substance, if the light is totally reflected back by that particular substance, then the substance appears white in color. Okay. If the light is totally absorbed by the particular substance and it is not reflecting anything, then the substance, it appears black in color. Now, if a part of light is absorbed and the rest is reflected back, then we see that that particular substance is colored. Now, based on this, you can see that suppose if a substance, it absorbs yellow, okay, and the rest is reflected back, what we see is the complementary color. We see the substance as violet in color. What you can see in the opposite of this color view, right? So this is what is happening in a when we are talking about colored substances. Okay, so we see the particular substance as violet in color. So this is what we understand by means of the color view. Okay. So now, if a substance absorbs light of a particular wavelength, so this, I think by now you know that I've already explained. So suppose if it absorbs a color, particular color, then we see the complementary color. Our eye will perceive the complementary color. Okay, so you can see the examples here. So here we have, if the color absorbed is violet, then we see the color, what our eye will perceive is the yellow-green in color. And these are the wavelengths which are given. Okay, the respective wavelengths have been given in this table. Okay, so you can just make a note of it. Okay. Okay, so these are the other examples. Okay, suppose if the substance absorbs blue color, then we see the yellow color. The substance appears yellow. Okay, if it absorbs greenish blue color, then the substance appears orange. So this is how the complementary color concept works as. Now, talking about Witt's chromophore-auxochrome theory. Okay, so what does it explain? So it explains how the organic compounds, how the color of the organic compounds, it is based on the resonance effect. Okay, so mainly we are talking about here the multiple bonds that are present, and when we are talking about how these bonds are in resonance with each other. And we know that especially when there are multiple bonds, there will be electronic excitation in the UV visible region, right? Because of which we can perceive the color. Now, when we're talking about the energy gap, okay, so if delta E is the energy gap, okay, if E1 is the energy in the ground state and E2 is the energy in the excited state, then delta E is the energy difference, which is nothing but E2 minus E1. So that is equal to H nu, which can also be written as nu is equal to C by lambda. So that's why HC by lambda. Now, if delta E, if this energy difference is very high, then high frequency is absorbed, right? We know that energy as well as the frequency, you can see here frequency is mu, right? Delta E and frequency, they are directly proportional to each other, right? Delta E is equal to H nu. So nu and delta E are directly proportional to each other. So if the energy gap is high, then the high frequency is absorbed. Now, we know that according to the other relation, you can see that delta E can also be written as Hc by lambda. So, lambda is nothing but wavelength. So, if delta E is higher, okay, if the energy difference between the two energy levels, ground state and the excited state is very high, then of course the wavelength is inversely proportional to the delta E, right? So the absorption occurs at a shorter wavelength, okay, because they are inversely proportional. Similarly, if delta E has a low value, then low frequency is absorbed and absorption occurs at a high frequency. It is inversely proportional. The wavelength and the energy are inversely proportional. So if delta E has low value, then the wavelength will be higher. Okay, so now when we're talking about a compound, okay, so there should be certain groups in the compound when we are talking about the color of the compounds. Okay, and these certain groups are called as color enhancing groups, which will enhance the color of the compound. So these are called as chromophores. Okay, chromo. Okay, when we are talking about chroma, okay, it is something related with color. Right, so chromophores are the groups that are present in a compound which will enhance the color of the compounds. Okay, so these groups usually they contain double or triple bonds. Okay, and more the number of such groups, deeper is the color of the compound. So we have examples: nitro group NO2. Okay, so here you can see there is a double bond, right? Here you can see the double bond, the presence of the double bond. Nitroso group, again there is a presence of a double bond. Azo group, again you can see there is a double bond. So usually they will contain the multiple bonds. Now, the compound which consists of a chromophore, which contains a chromophore, is called as a chromogen. Okay, so wherever these groups which will enhance the color of the particular, whenever they are present in a compound, that compound we call it as a special name, that is chromogen. Okay, now if there is conjugation, I hope you know there is alternative double bonds, okay, that are present along with these groups. Okay, as you already know, these groups contain the multiple bonds. Now, if there are conjugation, if they are conjugated with other double bonds, then the intensity of the color is more. Okay, so whenever we are talking about these chromophores, there is something extra which we are talking about auxochromes. So these are again different groups, okay, specific groups. When they are present along with the chromophores, they deepen the color. Okay, so when auxochromes are present along with the chromophores, they deepen the color of the compound. Okay, and these are essential groups for chromogens to act as dyes. So when we are talking about the chromogens, okay, whenever we are talking about a compound, okay, so if it has to act as a dye, those compounds have to contain this chromophores as well as the auxochromes. So whenever these auxochromes are present, of course, the color is enhanced. Okay, so example for the auxochromes: OH, OR, NH2, NHR. Okay, so these are a few examples. So whenever auxochromes are present along with chromophores, there is extra or deepened color. Okay, so when let us take a simple example, let us compare. So here you can see this particular compound is colorless. Here there is increased conjugation, right? Along with the double bonds are present. So this particular compound is pale yellow in color. Let us take other examples. So here you can see there is a lot of conjugation, right? So many conjugation. There are many double bonds which are conjugated with each other. It is nothing but beta carotene, which is orange red in color. It has a high intensity color. When I'm talking about 1,3-dinitronaphthalene, so this is naphthalene, and we have one in the one and the third position. We have the nitro groups. Okay, it is pale yellow color. Next, we have this 2,4-dinitro-1-naphthol, which is orange red in color because there is again an extra OH group. Right. Now, so I hope you know what is the role of OH in this particular example, in the third example, which is nothing but it is acting as an auxochrome. Right. So now, if the conjugation is increased, what happens? The absorption occurs at a longer wavelength. Okay. And because we know that energy and wavelength are inversely proportional to each other, if the absorption occurs at longer wavelength, then lesser energy is required, there is lesser gap, right, which is required for electron excitation. And this particular effect or this particular shift in the wavelength is called as bathochromic shift. Okay. Whenever we are talking about the reverse, okay, suppose if there is the shift in the wavelength towards a lower wavelength, shorter wavelength, then that shift is called as hypsochromic shift. So if the number of contributing structures is more, okay, then what happens? Lower will be the energy gap between the ground state and the excited state. And then the wavelength also affects, right? We know that the longer wavelength will be, the shift will be towards a longer wavelength, the energy gap will be lower, and deeper will be the color. Okay, so this is how these different aspects are related with each other. Let us take another example when I'm talking about nitrobenzene. So you can see here, these are the resonance structures, what are there in nitrobenzene, and the color of the nitrobenzene is yellow, right? Then we have para-nitroaniline. So along with the nitro, there is also NH2 group, okay, which will enhance the color. So of course, when you compare these two compounds, so nitrobenzene is yellow, whereas para-nitroaniline, you can see that intensity is higher. It is orange in color. Let us talk about synthesis of dyes. Quickly, let us look into how these dyes are prepared. So first of all, malachite green, how it is prepared. So the raw materials that are used is benzaldehyde and N, dimethyl aniline. So we know that this is, if we take this particular compound, this is aniline, right? Now the nitrogen, whatever the two hydrogens are present on the nitrogen, they are replaced by methyl groups. Okay, so in the N group, in the nitrogen, at the nitrogen atom, the two hydrogens are replaced by methyl groups, right? So that's why we name it as N, N. So at the nitrogen position, these substitutions have taken place. So N, N dimethyl aniline. Now, what happens here is, we know that this particular thing, here we know that there is a hydrogen here, there is also a hydrogen here, right? So these two hydrogens and this oxygen will be removed because you are using concentrated sulfuric acid, which is a dehydrating agent. It will remove a water molecule. So you get this particular compound. Okay, so there is a H, that is the hydrogen which is already attached to the carbon, and this particular carbon is attached to the two benzene rings of the N, N dimethyl aniline. Okay, so this is the leucobase, what you get. Now in the presence of PbO2, lead oxide, and in the presence of HCl, that is, we know that once you get the leucobase, you have to reoxidize it, right? So you get the color base. Okay, you can see that here at this position, there is a OH group that is added because you're going to oxidize it, right? Oxidation is nothing but the addition of oxygen, and in the presence of HCl, you get the malachite green. Okay, so this is how it takes place. Okay, so in the presence of HCl, of course, this OH group is removed off, and you can see there is the extended, the conjugation that is happening here with respect to this benzene ring. Okay, now let us talk about the formation, the synthesis of Congo red. So it consists of two important steps. The first step is formation of tetraazotized benzidine. Okay, so first of all, the raw material or the starting substance, what you're taking is benzidine here. Okay, it consists of two benzene rings connected to each other, and at the ends we have the amino groups. Okay, it is named as benzidine. Now, we know that whenever we use sodium nitrite in the presence of HCl and at a lower temperature of 0 to 5 degrees Celsius, this is an example of diazotization, right? We already know about this. So whenever we use sodium nitrite in the presence of HCl, okay, so you get HNO2. So here, the diazotization takes place at both the ends, okay, wherever there are NH2 groups. So here you can see, okay, here the diazotization has taken place. So you get the tetraazotized benzidine. Now, the next step is synthesis of Congo red. So you take tetraazotized benzidine, and along with that, you're going to take naphthylamine 4-sulfonic acid, two molecules of this. Okay, that is 2 moles of naphthylamine 4-sulfonic acid and 1 mole of tetraazotized benzidine. Okay, now we are going to join these both. So very simple here. Here we have chloro groups, right? And here there are the hydrogen atoms. Of course, we know that. So HCl and HCl will be removed off. So you get the Congo red. So we know that Congo red is synthesized on the fabric itself. So this is how it takes place. Okay. So this particular naphthylamine 4-sulfonic acid acts as a coupling agent. Okay. So first there is diazotization. So you get a diazotized tetraazotized benzidine, which undergoes coupling with the naphthylamine 4-sulfonic acid on the fabric itself, so that you get the Congo red dye. Next is the synthesis of alizarin. So you take anthracene here. The starting material is anthracene. Now, in the presence of oxidizing agent, K2Cr2O7, that is potassium dichromate, and in the presence of sulfuric acid, you get anthraquinone. Now, when you take this sulfuric acid and sulfur trioxide at 140 degrees Celsius, and then again you treat it with a base, you get first, before treating with the base, you get the sulfonic acid, right? So here, the sulfonic acid derivative, you get SO3H. Now, since you in the second step, you've added NaOH, sodium hydroxide, you get the sodium salt of the sulfonic acid derivative. Okay. Next, you add sodium hydroxide and sodium chloride in the and you fuse it, you get the alizarin dye. Okay. Finally, we are talking about how indigo is prepared. So we take aniline. Okay, this is aniline, and then we take the chloroacetic acid. So acetic acid is CH3COOH. So one of the hydrogen is replaced by chlorine atom. So we have chloroacetic acid. Okay, so this is chloroacetic acid. Now, again, very simple. Here NH2 has 2 hydrogens, and here there is chloro group. So chloro and 1 H will be removed off. So HCl is removed off. So we have N-phenyl, because in the N position there is a phenyl group. Okay, so N-phenyl, and this is nothing but glycine. Okay, glycine is an example for an amino acid, because there is amino group and also there is a acid group. Right, so this is an amino acid again, but substituted glycine, substituted amino acid. I hope you know what is the formula of glycine. So glycine is CH, and 2 hydrogens are there. In one end you have NH2, and in another end you have COOH. Okay. So here one of the hydrogens from the NH2 group is replaced by the benzene group, or the phenyl substituent. Okay. Now you add KOH in the presence of sodamide, I can call it, NaNH2. So cyclization reaction takes place to get indoxide, which on oxidation in the presence of nascent oxygen, it undergoes dimerization to form the indigo dye. Okay, so this is how the structure of the indigo dye is. Okay, I hope now it is clear about the synthesis of dyes, what are dyes, the characteristics of dyes, as well as the chromophore-auxochrome theory, okay, based on which we can decide about the intensity of the color and how the wavelength, the energy, how they are related with each other along with the frequency, and also about the synthesis of various types of dyes, and also how you can relate the different steps of synthesis towards the application of these dyes on the fabrics. Okay, thank you so much for watching. So don't forget to subscribe my channel for more informative videos. Thank you so much.